I can't believe that it's been 5 years. It's really hard to believe.
Because I live not too far from where Cronut lives at Six Flags in Vallejo, I really like to go out and visit him every once in a while to see how he's doing.
And because he's been doing so well, you look back and you're like, whoa, wait a minute. Okay, we were just doing that and now we're at 5 years.
I'm amazed when I see him. Now I think, how did this happen? But at the moment, I wasn't even questioning. I said, yes, let's go for it. And Scott was like, okay, so we both believe and everyone else believed and we're here.
He's so calm. I don't remember him being this calm in the past.
Hold it, Crow. Hold it, good job.
My name's Dr. Claire Simeone, and I'm a marine mammal veterinarian, and I'm Cronutt's veterinarian.
Hi, I'm Scott Baraban. I'm a professor and William K. Bose Endowed Chair in Neuroscience Research at the University of California, San Francisco. I direct an epilepsy research laboratory here that focuses on translational epilepsy research.
So my name is Mariana Casalia. Back in 2020, I was working in Scott Lab in the MGE project. We were trying to perform cell transplants to restore the brain function on animals with temporal lobe epilepsy.
So when you have a seizure, basically it's runaway excitation. In the brain of humans and all animals, we have two types of neurons. One are excitatory, and these make glutamate, which is an excitatory neurotransmitter. That's about 80% of the cells in our brain. The other set of cells are called interneurons. These are inhibitory cells that release GABA. GABA acts to reduce the excitation in the brain in the networks. In patients with epilepsy, and in temporal lobe epilepsy specifically, the hippocampus has a reorganization where some cells start to form new excitatory connections and other cells just get lost. Imagine having a car and you're going down the freeway and you tap the brakes. Normally that works fine, it stops the car. But in this case, when you have a seizure, you tap the brakes and it's not enough to stop it, and so it keeps going. And that's basically what the inhibitory cells are doing. So when you lose inhibitory cells, you're more prone to have these runaway seizure events. So my laboratory has always been interested in what these inhibitory cells are doing. There's a region of the embryo called the medial ganglionic eminence. Basically, the MGE contains what are called inhibitory progenitor cells, so cells that are destined to become these inhibitory interneurons. And that allows us to take cells before they've matured into that fate, put them into a host animal, allow them to migrate to where they need to be, and then integrate as functional inhibitory neurons. And so around 2000, 2001, for a couple of years, we studied just how these cells integrate in the brain. Of course, this is all mouse work, where we take the embryos from a mouse that has a fluorescent protein that glows green so we can find the cells, and we put those cells into a host animal. And what we found remarkably that these cells migrate a tremendous distance, almost covering the entire brain of the mouse. And more importantly, when we record them or look at their function, they act like mature inhibitory neurons that we were expecting. And more important than that, they actually talk to cells in the host brain and increase their level of inhibition. Unlike a sprinkler system where they're just releasing GABA, this inhibitory substance, all over the brain, they're selectively releasing it only onto the cells that they connect to. And so they actually integrate as new inhibitory cells. Drugs can't do this. So you can boost GABA function by giving a drug, but that goes everywhere in the brain. It's not selective. And so we were actually really excited to see this integration of the transplanted cells because it suggested that we got a very selective enhancement of inhibition that could be therapeutic and not cause a lot of side effects. And so restoring inhibition in the hippocampus allows you to cure these animals of their epilepsy as well as their comorbidities. And that allowed us to say this could potentially be developed for larger animals and potentially patients one day.
Cronut was not in the picture yet. We were just thinking on how to keep translating this work that in rodents was working fantastically.
So a large animal that actually has a naturally occurring epilepsy already exists. These are the California sea lions. The reason they have epilepsy is that due to global warming, there's a lot of high level of domoic acid in the oceans. Domoic acid is an excitotoxin. It kills excitatory cells. And so these sea lions ingest this as it gets into the food chain and develop temporal lobe epilepsy, similar to what you see in humans.
One day, Scott got a call about Cronutt. This sea lion was very sick. He had almost drowned a few times.
We were really trying all kinds of different treatments, therapies, nutritional support, all kinds of things. But because Cronut was not eating for extended periods of time, he was losing incredible amounts of weight. He was having seizures more and more frequently. At that point, we were having conversations about his quality of life, and really that it wasn't fair to him to go through all of this. And we were considering humane euthanasia at that point. And I talked to my husband, and he said, "You've got to reach out to Scott." He came and gave a presentation at the Marine Mammal Center about his work. The research that he's doing is amazing, and this might be one of the only options that Cronut has.
Early September 2020, during COVID, I received an email from Sean Johnson and his wife Claire Simeone about a rescued sea lion, a domoic acid poisoned sea lion named Cronut, who they had here at Six Flags. They were wondering if I can come out and maybe transplant Cronut with MG progenitor cells.
Scott is the best because he was very excited, but he was his typical, kind of reserved and calm self of, yeah, we can absolutely do that, and so he told me the details about, his colleagues and everything that had gone into all of the research at that point, from, studying skulls of sea lions in California Academy of Sciences to developing a really specialized needle to be able to transplant the cells. And so all of this research and all of these steps had already taken place. And I can't speak for Scott, but I know that everybody on the team at Six Flags was really, really excited that there potentially was one more option. Because anytime we're talking about humane euthanasia, that's just a really sad conversation, because these are animals that you've cared for years, and that everybody has a relationship with.
And so they said, sure, let's go for it. I went home and started about 4 different separate email chains, coordinating the various groups of people that would need to come together to make this happen. The neurosurgeons in my team in my laboratory, the veterinarians, anesthesiologists, etc., the handlers here from Six Flags, and then a 4th one just for the logistics of getting us all to the same place for the procedure.
As soon as we learned, we started to get everything ready. We started to harvest more cells.
So in less than a month, we all gathered in South San Francisco at a vet clinic during COVID in the parking lot. Cronut arrived in a U-Haul in a crate and was prepped for surgery in the parking lot, because the vet clinic, again during COVID, was only allowed 5 people inside at a time. So a lot of the work had to be done outside the vet clinic, and then we had to rotate who went inside to work with him. A couple hours went by, he was prepped for surgery, he went inside, got an MRI, a CAT scan, had a device fitted by the neurosurgeons for the procedure. Mariana prepared the MG progenitor cells for transplant. A couple hours later, watching on a video on an iPad with Diane Cameron, who was his handler at the time, holding my hand, they injected the cells into Cronut, and a few minutes later, he was good to go. Diane was crying the whole time. Cronut came back out, got into his crate, and drove home here to Vallejo. And the first couple months after his transplant procedure, I came out about every month just to see how he was doing, to see how he was recovering. Around 1 year, his handlers here started to say he was acting like a normal sea lion. He hadn't had any seizures, he wasn't having any complications, and he was starting to regain some of his cognitive abilities.
He's like about 12 years old now. He's a man. He's right? Good job, Cronut. And I think about all of the bonus years that he got, and that's so cool. I think we were all focused on the procedure itself in 2020 and everything that took, but then to just see him living his life and having a good time is so cool. It's so cool to see.
We're going to interview him. You have any questions for Cronut?
Any questions for Cronut?
Cronut, how you feeling? It's a wonderful journey we've been on. To see him happy and healthy and thriving based on simple, I don't want to say simple, but based on experimental research we do in a laboratory, and to see that translated to a marine mammal, it's incredibly rewarding.
Research is an act of faith. is not real until you make it happen. Everything that you're working on, it doesn't really exist until you make it happen. We really believed in this and we went for it and we make it happen, and everyone around us followed. And this is why we're here.